Greetings and welcome to part 2 of the Introduction to Ethical Hacking. In this section, we are going to speak about the networking fundamentals. Knowing how to hack is great, but if we do not know how to connect to a target machine or which protocol to use, our knowledge will be pointless. If you already know all about IP addresses, MAC addresses, and subnetting, you probably can either skip this section or use it as a refresher. An IP address is what every device uses in order to communicate between each other via the router. Think of it like a postal address, where every network packet is an individual mail and the router is the postman. Since every device possesses an IP address, it means we got one too. To find out which IP address you have been assigned, you should open a command prompt and type in the command ipconfig. And here is our IP address. You probably did not assign this IP address on your own, otherwise you will already know all about the basics of networking. Instead, the device that most likely attributed this IP address is your home router. Every time a device requests an IP address, it will use a service on the router called DHCP that will dynamically assign IPs. In the ipconfig prompt, we have an IP address, a network mask, and a default gateway. The default gateway is the IP address of your router. Whenever a device needs to communicate to something outside of its network, it will send its packets to the default gateway and the router will handle it by itself. As it is a router, its goal is to route packets. The 255 part of the subnet mask simply explains how many hosts can be on the network. If only the last number equates to 0, it means that only 255 addresses can exist within the network. Bear in mind that in every network, two addresses will always be reserved, 0 and 255. 0 being the default gateway and 255 being the broadcast address, which is an address used when a packet needs to be sent to every device within the network. Ultimately, it means that in a 255.255.255.0 subnet mask, one can assign 253 addresses per host and per network. An easier way to note the subnet mask is with the CIDR, which is a prefix notation. For example, 192.168.1.1/24 means 255.255.255.0 in reality. You can look up a correspondence table and use the CIDR instead. If you are wondering why the maximum number is 255, it actually is quite simple. Computers function with 1 and 0s, either on or off, because this is how electricity functions. And computers communicate with octets, meaning a set of 8 on or off states, called individually bits, and 8 bits set to 1 equals 255. If you don't trust me, let's look at it together. We will populate an octet from 8 zeros to 8 ones. In order to count, we have to populate all available zeros into a 1 from right to left. When every zeros are populated, we shift to the left and put everything else back to 0. If what I just said did not make any sense to you, here is a table to show you how it works. Let's take the number 7, for example. 7 is less than 8, so we don't take that number and put 0 instead. 7 is more than 4, so we take that number. 7 minus 4 is 3, so we put 1 once again. 3 minus 2 equals 1, and 1 minus 1 is 0. So in binary, 7 is 0, 1, 1, 1. Let's expand this table to 8 bits, and it now becomes abundantly clear that all those bits flipped to 1 equates to 255. The format of IP addresses shown so far is called IPv4. Since it uses 4 packets of 8 bits, we have 32 bits either on or off, which makes it 2 to the power of 32, which equates to around 4 billion individual IP addresses. Not only are we 8 billions on the planet, but all public IPv4 addresses are already registered. To counter that issue, we have what is called the IPv6 format. The issue with this format is that it is quite complicated to write, and administering a network with such a format can be a mess. So we have something called Network Address Translation, or NAT for short. Thanks to NAT, Your home router possesses a single public IP address, and any contact you make to the outside world will be used with this single IP address. Every device that can communicate on the network can do so because they have a network interface controller, also called NIC, and NICs have their own type of addresses called MAC addresses. A MAC address format is in two parts. The first part is the OUI, and the second part is the NIC. The OUI is vendor specific, meaning that just by reading a MAC address, we can know what kind of device it is. MAC addresses are used for switching. If you have ever plugged your computer to an Ethernet port, but wondered how your router knows that this specific cable is the one it should use to send its packets, now you know. There are two main network protocols we use every day, and those are TCP and UDP. TCP stands for Transmission Control Protocol and is used when it is important that the packets you receive are correct. For example, when you download a file from the internet, the network needs to constantly check that it sends the correct packets and that nothing went missing in the middle of the transfer. This adds a lot of overhead because there is a constant back and forth communication between you and the server that serves the file you want to download. This back and forth is what we call the three-way handshake, which is composed of a SYN, a SYN-ACK, and an ACK. For example, when you visit a website, you first request to connect to the website by sending a SYN packet. You are ultimately requesting to synchronize with the web server. The web server then agrees with a SYN-ACK. It acknowledges the synchronization and then you answer ACK, confirming that you received the agreement, and only then can the web server show you the website. Sometimes we simply do not need this overhead. For example, if you watch a stream, the communication is done using UDP, because this is not extremely important if a packet or two is missing. The most important is that there is a constant flow of data that arrives to you so you can watch the stream. If we have a server and we wish to host multiple services on it, let's say a website and a mail server, how does the server know which service we want to access? Well, this is thanks to ports. A port is a sort of virtual gate that you can open or close to offer a service. Usually websites are hosted on port 80 or 443, so when you contact a website you are actually calling port 80 if it is HTTP, and port 443 if it is HTTPS. But if you wish to contact the mail server instead, you might call port 25, for example. On port 53, we have DNS, also known as Domain Name System. DNS is what enables you to see google.com as google.com and not as an IP address. Think of DNS as a phone book. When you type google.com, you are actually contacting a DNS server that has correspondence list of IP address and domain names. When it receives a query for google.com, it searches through its databases what this name refers to and provides your web browser with the correct IP address. Just imagine how unusable the internet will be without DNS. So, we know what IP addresses are, and we also know what ports and protocols are. That's great, but if we are targeting a single machine, what about networks of machines? See, there is such a thing as subnetting, which enables us to create multiple networks in order to logically separate some machines from one another. The reasons for subnetting are plentiful, but the short answer is that in some networks, specific machines do not have to communicate with the others. Separating them means less traffic on a specific subnetwork and the added benefit of security. If someone has access to your computer, they cannot then transfer to the other unless they find a device that has access to both subnets at the same time. Now that we know why subnetting is interesting, let's do some subnetting. Our client asks us to create 3 networks, and the network ID is 192.168.4.0/24. Thanks to this table, we will be able to create them. Remember, we need to create 3 separate networks. In the subnet row, we have either 2 or 4, but not 3. Since we need at least 3 networks, we will have to use the column containing 4 subnets. With 4 subnets, we can have 64 hosts, and our subnet mask is going to be a /26. With this information alone, we can create our network. The original network ID that was provided to us was 192.168.4.0, and within our table we saw that we could have 64 hosts per network. So logically, the next network ID is going to be 192.168.4.64, then 128 and 192. Our subnet mask is always /26. The number of usable hosts is 64 minus 1 for the network ID and minus 1 again for the broadcast ID, which leaves us with 62 usable hosts. The network ID is always the first number in the network, and the broadcast ID is always the last one. Knowing that, and also knowing that 0 is also a number, the broadcast ID is always going to be the network ID plus the number of usable hosts plus 1. For example, 192.168.4.0 plus 62 plus 1, which gives out 192.168.4.63. Then 192.168.4.64 plus 62 plus 1, which gives out 192.168.4.127. By the same logic, we end up with 191 and 255. The host ID range is simply the range of hosts that are between the network ID and the broadcast ID. For the first row, the range is 192.168.4.1 to 192.168.4.62, then 192.168.4.65 to 192.168.4.126, then 129, 190, and then 193 to 254. Easy, right? Try to redo this exercise with another requirement in order to make sure that you got it. The last subject in this chapter is the OSI model. The OSI model is a way to represent the different layers a packet goes through from start to finish. It helps not only to understand what is required for an information to go from a simple wire down to being displayed on the screen for a video game, for example. This model also helps to troubleshoot problems. If your internet connectivity does not function, it will be most logical to first check at layer 1 and go up, then the other way. It goes both ways, of course, meaning that when you perform an action on your computer that requires you to send some information remotely, the information is going from layer 7 to layer 1 on your computer, and then from layer 1 to layer 7 on the remote computer. Great! Now we understand how machines communicate between each other. In the next chapter, we are going to install our own hacking machine.